So in this question here, we've been given sine theta is a over b, and it's in quadrant 1. So I'm going to first draw that out. Okay, now whenever I draw of some ratio, I don't want to draw it at 45 degrees because that's going to imply that there's some symmetry involved. So in this case here, I'm just going to draw the a over b like this. So there's my a, there's my b. Okay, so there's my angle theta. Now what I want to do is I want to find the tan of theta plus 90 degrees. Now I can do this geometrically because I can actually draw a 90-degree positional change from here to here. And that's going to give me this triangle, which matches the original triangle. If that matches the original triangle, the lengths are the same. We just have to account for the positioning. So the horizontal length of that red triangle is the same as the vertical length of the black triangle. So it's a, but it's going to the left, so I have to write this as negative a. The radius stays the same, it's b. And then I can work out this side here using Pythagoras. It's going to be b squared minus negative a squared, which is, I'm just going to write as a squared. And once I have this red triangle, really I have this angle position represents theta plus 90 degrees. So if I want to write the tan of theta plus 90 degrees, I can just use that triangle. Tan of theta plus 90 degrees is going to be that triangle. It's going to be the slope of that triangle, which is rise. In this case, the rise is going to be b squared minus a squared square root. And the run is going to be negative a. So we have a negative slope. Yeah, that line is a negative slope. And that represents my tan value for that new position. So I can find 90-degree rotations using this, 90-degree rotational positions using this kind of strategy. For this one here, we want to solve this. So to solve this, we first need to recognize that we have a quadratic. So we need to first of all solve the quadratic. Then we need to solve for the ratio. Okay, and because we're dealing with cosecant, we probably should at some point change this to sine. So first things first, I need to solve this quadratic. I need to factor this. So this becomes cosecant theta. Two numbers that multiply to 2 and add to negative 1 are going to be negative 2 and positive 1. That's equal to 0, so I can solve those independently. So I can solve this equation by saying that cosecant theta is equal to 2. Here, cosecant theta is equal to negative 1. Now, I don't know my cosecants that well, so I'm going to convert this to sine. So sine theta is equal to 1/2. Cosecant, when I flip that around, that still stays negative 1. Well, now I can solve this. Because these are special angle ratios, I can just solve this without a calculator. So sine theta equals positive 1/2 is going to end up here at 30 degrees and at 150 degrees. So theta is equal to pi over 6 and 5 pi over 6. Those are those two positions. For this one here, sine is going to be negative 1. Sine is negative 1. Sine is the vertical position. It's going to be at the bottom of the circle. And there is no theta 2 here, so there's only one solution, and it's going to be at 3 pi over 2. This question asks for 1 period worth of solutions, so it actually asks between 0 and 2 pi, which represents 1 period of solutions for this particular function. So we're just going to leave those 3 solutions. Again, we can check this on Desmos, but we can just graph and we'll see that there's 3 solutions between 0 and 2 pi. In fact, you'll see that it will bounce at 3 pi over 2, because they're usually two solutions, but they end up being compressed into one spot, so we end up with a bounce on the x-axis.